Ever wondered how to predict the power output of a combined cycle power plant? Today you're in for a treat. Picture a power plant humming with energy, surrounded by a wealth of data from environmental sensors. These sensors monitor temperature, ambient pressure, relative humidity, and exhaust vacuum, all critical factors impacting the plant's electrical energy output. But how do you go from sensor readings to power output predictions? That's where machine learning comes into play. The task at hand is a regression task, predicting a continuous value based on certain features. In layman's terms, regression is about making an educated guess on a quantity that can take on any value within a range, given some information or features. For our power plant, we're trying to estimate the electrical energy output using sensor readings as our features. There's no one-size-fits-all algorithm for regression. Some common ones include linear regression, random forest regression, and support vector regression, or SVR. Each has its strengths and weaknesses, so it's about finding the one that best fits our data. Now, how do we measure how well our model is doing? Enter mean squared error, or MSE. MSE calculates the average squared difference between the actual and predicted power output values. The lower the MSE, the better our model is doing. So, armed with the knowledge of regression, possible algorithms, and evaluation metric, we are ready to delve deeper. Our dataset comprises of 4 key features: temperature, ambient pressure, relative humidity, and exhaust vacuum. These factors play a crucial role in determining the power output of a combined cycle power plant. There are several algorithms we could use for our regression task, such as linear regression, random forest regression, and support vector regression. Each one has its strengths and weaknesses, but all are capable of providing valuable insights. Now, on to data splitting. This is a key step in any machine learning project, allowing us to train our model and then test its performance on unseen data. Typically, we divide our data set into 3 parts: a training set, which comprises around 70% of the data, a validation set, which takes up about 15%, and a test set, also comprising roughly 15%. With the data duly split, we can now proceed to the core of our project: model comparison and selection. With data in hand and algorithms in mind, it's time to train and compare our models. The journey of model comparison is a blend of experimentation and intuition. We may choose to compare different algorithms such as linear regression and random forest using identical features. Alternatively, we can play around with the same algorithm but with different feature combinations. It's like trying on different outfits to see which one fits best. Further, we can also delve into the world of hyperparameters. For instance, we might experiment with the number of trees in a random forest model to see how it impacts our results. Remember, our goal is to find the model that delivers the lowest mean squared error on the validation set. It's a process of trial and error, but it's well worth the effort. After all the comparisons and selections, we would have our final model ready for evaluation. Now that we have our final model, it's time to put it to the test. We've come a long way, selecting our features, choosing the right algorithms, and splitting our data. But now comes the moment of truth. We're going to train our chosen model on the entire training set. This is where all the sensor readings, temperature, ambient pressure, relative humidity, and exhaust vacuum come into play. This is the last and final round of training before we unleash our model on the unseen test set. Remember, this test set is our unbiased judge. It's data that the model hasn't seen before, making it an excellent measure of how well our model can generalize its learning to new, unseen data. Once the model is trained, we evaluate its performance on this test set by calculating the mean squared error, or MSE. The MSE is a measure of how accurately our model predicts the power output of the power plant. It's calculated by taking the average of the squared differences between the actual and predicted power output values. The lower the MSE, the better our model is at predicting. This is the moment where we see if all our hard work has paid off. If our MSE is low, we know we've built a robust, reliable model. And there you have it, a complete guide to predicting the power output of a combined cycle power plant using machine learning. The power of prediction, isn't it fascinating?